I'll draw my slide. I know it's on there.
All right, going on. Today is, I believe it's lecture number, whoops, let me do this. Lecture number 15, last of the semester. So we are going to have presentations, 2 to 3 minutes, and then we will wrap up for the end of the class, and we will, without further ado, start up. Is that presentation?
Hi, my name is Riju. I'll be speaking on multi-robot SLAM and map merging. Now the thing is, once the SLAM concept has been deployed onto a robot, the logical next step would be to upgrade it so that multiple robots can simultaneously use SLAM and share the information with each other. That's where the scan matching SLAM concept comes into place. The main aim of this is to find the most likely global map. Now, when multiple robots are deployed on the field, if the relative positions of each is known to the other, then it becomes fairly easy for it to share this information and map a global map. But the thing is, that's not true in most of the cases. That is, the robots are not aware of where the other robots have been deployed. So what needs to be done is the robots, they use the SLAM technique to figure out and judge the surroundings around them and to create a map and find out the most prominent structure and call that as the frame of reference. Once this frame of reference has been found, then they can use this to form a global map. You can see here is there are those two horizontal corridors where robots are placed on either end of the corridors. This is the SLAM output by one of the robots. It is able to detect the corridor and the vertical corridor. And this is what happens in case of the second robot. Now this vertical corridor becomes the frame of reference. So using this, both the robots are able to form a global map. So this is the concept of multi-robot SLAM and map merging. Any questions?
All right, next.
For mobile robots using laser rangefinders and molecular vision. And this is done in China at the Harvard Institute of Technology. What they did is that they did this experiment on an autonomous robot using a CMOS camera and optical mica. Also, they used radio Ethernet. They use the weighted least square fitting, which is a method used to estimate systems, as well as a Kalman filtering KF to localize and to use the grid map building simulation. And the Canyon operator, which is an edge detecting operator, it's used for multi-stage algorithm to detect wide range of edges in an image. And this is the map that they have used the robot in.
Do they have any graphical representation of their what they came up with?
No, No, the paper included the statistical data and the equation that they used. They didn't have any graphs.
No results, right?
Right.
All right, next.
Thank you.
Next.
Sorry.
Hunter. After Hunter is Hill.
My presentation today on SLAM with using RFID tags, and the technique that they use, it's brought about by some research from the Intel Research Lab, and it's a couple of people from, I think, Stanford and Washington University that were working on it. They have a robot that they set up with a laser range scanner and 2 RFID antennas on the robot, and they will use some maps that they previously learned from the laser range data. So they'll take those maps, and based on what it finds, it'll then use the RFID antennas to gather the location information that it's putting out as it gets close to the RFID tags. And then from there, it'll start to estimate the RFID locations, and which that's shown in the first picture, where they set up just kind of the hallway in the office building. They set RFID tags up on the corners of just the cubes. They stack them here, just something on the edge to say, hey, here's an edge of something, and then when it reads the RFID, it'll say there's the location of it. So it'll start to estimate that the tag's locations based on the map that it just picked up, and from there, it'll start to use the Monte Carlo localization technique to guess its own location and pose, and from there it'll start to plan its own route and what it thinks it needs to do, which is the second picture. And the third picture is the route that it would actually end up taking, the actual ground map of how it would go. Knowledge. Some of the benefits of using this type would be that it reduces time for localization, because the time that it takes to read the RFID tags and get them back is much quicker than using some other techniques. And you could also, if you were to use the RFID tags on other moving objects, you could localize them fairly quickly because of that time decrease. They're also fairly low cost to implement. The RFID tags are, because they're relatively cheap and getting cheaper. But some of the cons are that the energy needed by the RFID tags that are placed on everything, some of the energy that they need can be absorbed by the metals that are around the different materials, and it can also be affected by the angle of the RFID tag based on where the reader is. So sometimes it's not the most accurate of methods based on those 2 factors. And also you have to stack RFID tags on everything, which would be kind of annoying. But that was their kind of quick way of doing it at the Intel Research Lab. Are there any questions?
Are those active or passive RFID tags?
They would be passive because they need electricity from the reader.
Okay. So since they're passive, then they really don't need their own batteries. So really the problem of localization is not so much at the little tag side, it's more at the reader side, is what you're saying, right?
Yes.
Okay.
The tags just have a little bit of location information based on where they're placed. And then when it reads it, it'll take that and use its own map to kind of guess more accurately where they are.
And this is only localization because the map's already built, right?
Well, you're using the laser range scanner to build the map as you're going through it.
But this is mostly localization because it already knows where it is.
Yeah, it's more localization.
Okay. Or it already knows what it's supposed to look like. Okay.
Any other questions?
Hill, and on deck is Finney.
I'm going to do my presentation on Rhino, which is a high-speed mapping and navigation robot. In the lower left corner, you can see the actual Rhino robot because its head looks kind of like a rhino. It's able to map, localize, and also navigate For mapping, it uses two different types of methods at the same time. It uses grid-based maps and it uses topological maps. For the grid-based map, it's more like when we did the A-star planning where it breaks everything up into a grid. And it also uses a stereo camera, which is a camera that can actually take a picture of the environment and then just take the edges out of everything into finding where the depth is in the actual picture it sees. And then integration is when you put those two together to create the grid-based map. For topological maps, you can see it in the right over here, where it actually breaks up the map into units, into critical points, and then it draws lines which are critical lines to show it which sections it can move in, and it maps out the whole entire area. In the center, you can actually see the ultrasound where it uses both the stereo camera and the ultrasonic sonar. The sonar is the one on the left for part A, and part B is when you add in the occupancy values. It's a digital reading, so it takes what it sees from the ultrasound and then it converts it into an occupancy, whether it's occupying it or not, and that's an example of a corridor. For localization, it uses wheel encoders. It matches the map of global and local, and it also uses sonar modeling to figure out the maneuverability, wall orientation, and landmarks. And the reason why it uses landmarks is so that when it gets to a certain point, that it can understand where it is and go from there. As far as navigation, it has what it calls a global planner, which plans out the whole map. As you can see from the example of topological, but if someone were to put like a random obstacle in the way, then the collision avoidance would kick in and would actually send a reading to override that. And also has hard constraints and soft constraints. Hard constraints are things like, I want to say it was clearances and things like that where it could not go beyond a certain point, and soft constraints were objects that it could possibly go over. And in the lower right corner, I have an example of how it uses its navigation system for an event that people are randomly in a hallway when they weren't there before. So, any questions?
On deck is Doan.
I'm presenting today on Stanley. We've seen some presentations on this. It's the robot that Stanford put together for the DARPA Grand Challenge. So the paper I'm referencing is called Probabilistic Terrain Analysis for High-Speed Desert Driving. And interesting note, the guy, the author of this is now the director of Google's autonomous vehicle program. And that's how he got the job, because he won the Grand Challenge and this prize. So the keyword high-speed desert driving, that was what's really cool about this. He came up with a software algorithm that allowed the vehicle to go faster than any of the vehicles in the challenge, and also without hitting anything. So how do you do that? He came up with this algorithm, and pretty much standard with the other robots. He used 5 LiDARs for 3D mapping, inertial guidance, GPS waypoints. But the color video camera was one of the key components, and what they realized was that the LiDAR can give you about 30 meters of readability, so you can see 30 meters out with LiDAR, but it's not far enough to drive fast, so you got to look farther to drive fast. So he used a video camera which looks to the horizon, and he created a software algorithm, so it takes your 3D LiDAR of what's in front of the vehicle, and it compresses that to a 2D map, and chops that into a 30 by 30 centimeter cell in a grid. So you have a grid with all these 30 by 30 centimeter cells. So then the LiDAR and the other sensors, you can designate each one of these cells as drivable, obstacle, or unknown. And it compares the cells that were created by the LiDAR the readings with another piece of information which was given out by the video. So you take the video and say, let's, for instance, you identify one cell in this LiDAR array of data as drivable. You map that to your video, and you find that specific cell in the video data, and you map that as drivable as well. So then it's actually called machine learning. So then the machine can start taking the video data and estimating, well, based on what I know about this LiDAR data and what a drivable portion of the video data looks like. I can estimate the rest of the video. So it allowed him to speed the vehicle up because it could use the video data much more efficiently and quickly than it could the LiDAR data. So, yeah, that's about it. Any questions?
On deck, De Los Santos.
Today I'm presenting a lightweight slam algorithm for indoor environment. The big assumption that for this slam algorithm is orthogonality. So because the slam, this slam techniques was developed for indoor movement of the indoor slam of the robot. It's assumed that most of the major features of the environments are either perpendicular or parallels. And at the bottom of the slide is the algorithm. What it does is it has the laser rangefinder to take the 3D raw data, and then the 2D line extraction will extract the 2D raw data into a 2D line segment. Using this SLAM techniques, it assumes that the planes or lines can be represented by a horizontal lines. The 3D lines calculation basically convert the 2D line segment into the 3D line segment, and orthogonal lineation correct the line segment that are not perfectly orthogonal, and maybe slightly deviated. Using this technique, the robot can detect out the planes that are in the figure second from the top, and the figure on the last is the this one is the construction drawing of the hallway, and this one is a map is produced by the robot using the SLAM technique.
Any questions?
Rapid 3D mapping. 3D maps gives you an overview of a location while giving you a schematic angle view of the route ahead of you. The rapid 3D mapping system generates three-dimensional imaging capture of the terrain via aircraft, helicopter, or unmanned air vehicle. Rapid 3D mapping makes possible to generate this 3D mapping, three-dimensional map, within hours of the flight, and the results of that mapping depends on what sensors were used on the aircraft to capture the data. The typical coverage of one of these airplanes will be of 100 kilometers square per hour with a resolution of 0.01 meters at ground level. There's 3 steps for superior awareness, which is flight, generate, and view. As I said before, the flight can fly at altitude of half kilometer with a resolution of 10 centimeters or 0.01 meters. The flight time is about 1 hour, and it covers 1 kilometer square. The generation of these maps is fully automatic, and the processing time is 5 times the flight time. So it took 1 hour, it will take up to 5 hours to generate the 3D mapping of the area. After that, it sorts the images, extract the 3D information, and then it applies the textures and buildings and terrain classification. And then the view, those 3D images or 3D map will be georeferenced at a very high detail of accuracy of 0.03 meters. And I'll show you a video of it.
I think you asked me a question if showing the video counts against your 3 minutes, and it
Yes,
does.
it does.
I didn't understand your question earlier, so.
Okay. I will.
You're so slow, guess it's not.
I'll give them a break for that. Oh my gosh. This thing takes forever. The commercial doesn't count against it either, right?
I think that's the game.
Got that.
Oh, okay.
That's how it covers the terrain. It could be on any other platform. You can see that it will extract the 3D information from the generated from the aircraft and then apply the textures and classify the terrain.
So what's that right there?
That will be San Francisco.
That's I think it's Alcatraz.
Yeah. Well, I mean, that's, and then there's this one, which is the applications that it can be used on. Usually, it's for military purposes as of right now, because it's just declassified information technology. So as you can see, you can plan the route, and it could tell the difference in terrain from 1 day before or 2 days before from the one that it's taking at the same time. So you'll see there's difference, and then it can give you different routes to avoid line of sight of what probably enemies could be. See, as you can see right here, there's the helicopter or the unmanned vehicle scanning the terrain while in real time transmitting the 3D data to the vehicle behind it. Well, it's your reference, and as you can see, this last one, it can detect the difference from 1 day ago and tell you that there could be something there. Then they perform a thermal imaging and find, kill whoever's there.
Destroy.
So,
Chew, you're on deck.
I'm Scott Collins, and I did my SLAM presentation on IMU and LiDAR. It's basically just two sensors put together to create the mapping technique. To go into IMU a little bit, the IMU is an acronym that stands for Inertial Measurement Unit. Basically, it is 3 gyroscopes and 3 accelerometers, both of which measure the X, Y, and Z. All of which measure the X, Y, and Z axis, one for each. Gyroscopes is this little image here on the right. This is a Hubble gyroscope, which, if the rotor is spinning, it creates a balance per se, and that creates a resistive force to any kind of movement. With that force, you can measure pitch, roll, and yaw. Airplane pitch is down, side to side is roll, and yaw is twisting about the top, spinning around basically. Put that together with accelerometers, which measures acceleration. There's a number of different ways they can do it, but basically a force is measured from a mass over there on the right-hand side, connected to springs. Can measure voltages or what have you, and it determines a force, which from there it can determine an acceleration. You put the two together, and you can come up with a position, an orientation and a position in a plane. I mean, in a space. Then you have LiDAR. If you add LiDAR with that, LiDAR is basically just lights, and it measures the speed of light, the distance to travel to an object and back. It can measure at 360 degrees continuously, They also have them that do 3D. The ones that I found were using 2D LiDAR, so based on the way the orientation of the unit, it could tell the, you know, walls and all that kind of good stuff. And I have a, if I can get to it, an example. Let's see what happens. Of a gyro. I'll show you a couple of those. Some uses of it. This is not a gyro.
Skip ad.
Okay, so basically he's got it spinning. If you spin this rotor, it creates a balance. It's resisting force in any direction, and it'll pretty much balance in any position. Uses in an airplane, for instance, they measure, you'll see it here, they have gyros mounted inside of fixed shafts, and through the use of these sensors here, they can measure the position of the plane. You'll see it start to turn, and based on this position of this gyro, which will always stay perpendicular, or up and down. And through that, they can come up with the pitch, roll, and the yaw of the plane. Let's see if I can get it here. And then, here is an example where they use the two together, the LiDAR and the inertial measurement units. You can see over here on the right, it is mapping out the hallways. The red line is where he stands in the hallway. You'll see it curve a little bit as he's walking based on position, and the IMU and then the LiDAR is sending out light beams back and forth off walls. And he, for the most part, maps the entire corridor of these hallways in this building, stores it in memory, and can use it for future references.
He must have one fast computer.
And that's it. Any questions?
This presentation, I'm going to talk about the demonstration of 3D SLAM capability of a robot using IRSP, which stands for Intelligent Robotic Software Platform. All right, and I'm going to show you this video real quick. All right. So basically, this demonstration is the map data is updated from the calculated position of the robot using simulated onboard range sensor, and the robot using a demonstration can be driven under two drive modes, which is automatic and non-automatic. For non-automatic, that the user controls the speed and the direction of the robot, and for automatic, the robot is just given the final position, the final destination of, and the robot will generate the path that goes through the space, just like our lap 5, and if the map is updated and blocks the generated path, the robot will immediately regenerate the path, so it's not going across the blocked area. And there are 8 sonar sensors to measure distance, and they use this device that invented by ASUS, which is called Action Pro or something, and it has a range of 0.8 meters to 3.5 meters. It's kind of like Kinect, and it created a 3D map view over there. And there's another direction sensor which can accurately navigate throughout the path, and which is driven by 2 DC motor with an incremental encoder. That's it. So,
Any questions?
give my presentation on the intelligent technologies for SLAM. SLAM's all well and good, but if you can't relate it to your robot and use it for your advantage, then it's just like a technology that's gone to waste, basically. So some of the other things that they've been working in to work with SLAM and ways to make SLAM work better are shown up here. They're developing a sensor right now that will detect human neural patterns and things, and that's how it'll locate humans in an area. So that's one way that it'll work with SLAM. It'll be able to avoid, the robot will be able to avoid the humans in a hallway by sensing their neural network and stuff. And then SLAM just basically maps unknown locations. So a lot of times, if you're mapping and mapping unknown locations, but if you're localizing, you usually have a map. I think that the robot already knows. They've been looking into using like a type of gas and infrared sensor that will spread out across through the area, and then the infrared sensor will scan the gas as it envelops the room, and then it'll be able to map the room like that. So I thought that was pretty interesting. And then the bottom 2 points, evidence supporting measure of similarity and a unified fusion approach are 2 ways just to make SLAM better, basically. And EMS just is like the bottom picture down there. It takes a whole bunch of data and collects it all together, and then it's able to take out the points that don't matter. So it's outlier detection and rejection, basically. And it's able to select only a subset of data that is needed at a specific time. And then the unified fission approach is taking multiple sensors and then making them all work together. So the Department of Defense uses it a lot for automated target recognition, surveillance, and guidance and control. And then the industry uses it for monitoring complex machinery and medical diagnoses and smart buildings and things like that. So.
Any questions?
So this is on Atlas. It's actually an algorithm that uses SLAM to do a larger global optimized map. Basically, it uses things like, I'm not going to pronounce SLAM right, but Dijkstra, shortest path, which uses basically a method that creates a tree, so you have a starting vertex, and then it creates a tree from each vertex that's by distance, ordered by distance down, so you know the direct path, how long you're taking to get from one to the next. But what Atlas does, it takes things like that, and then it combines them based on a graphing method. So the robot has a position and sets up a graph, and then when it moves to the next one, it then uses the outline from the first one to help with the next mapping of the next segment. The way it does that is through local region SLAM, so we do take each local map and then combine it with the next one. The map frame hypothesis, the other thing it does, it has a juvenile map, a mature, dominant, and retired, and what those mean is the juvenile one doesn't have enough data points collected in order to make a full map, so it doesn't use it yet, but it can mature based on the local SLAM into a mature map, and then once it does that, it can use that to kind of establish its surroundings. The dominant is just that if it's gone back to a place or something before, the first map is the dominant map, and the retired is if the mature map doesn't qualify enough points, then it can be retired and then just it gets deleted. So there's always a mature map and never anything more than that. They have 2 different ways to visualize it through this map, the global optimized map and then an Atlas graph. The Atlas graph is just basically the lines of which way the graphs are going and things like that. The results, they did a test of what they call the infinity hallway at MIT. They're the ones who came up with this Atlas mapping. And this is a map of their infinity hallway. And it took 101 map frames and 15 map line segments to complete it. And so they're allowed to do that. And they are trying to implement it into a lot of UAVs and things like that, and ideally into underwater mapping, because you can use that for that. So that's all. Any questions?
John,
He's outside.
what the heck? Go to the next one. Go to the next one.
Right here. John, you're up.
Oh. 9, 8.
He's doing views.
All right, Wesley.
I did my SLAM topic on the Mars rover, SLAM techniques. It uses Summit. I'm going to let you read the acronym there. It won't take too long for me to read it. But it uses 3 sets of fixed cameras using stereoscopic vision, which is what humans use in order to determine depth. And each camera will take this stereoscopic image and develop a disparity map. And what this concept is like if you're watching a 3D movie without the glasses, that's kind of the concept. It'll calculate the distance between each pixel on the 2 images that match up with each other in order to create a 2D model, sort of 2D, 3D model. And then it'll take the images from all of the sets of cameras, combine them all together, and then you've got this bunch of points in a 3-dimensional space called a point cloud model. And then after that, you connect the dots and you've got a bunch of polygons, which is pretty much your surface. And the algorithm they use is shown here on the right. It's, you can look through that so you can figure it out, but starting from the left, you've got the left and right stereo images going through the correlator, producing the disparity map, putting in the point cloud, and then going through some data structure stuff, and then finally producing the polygon models. And in terms of localization, the rover has an IMU and a motor encoder. And in terms of software, it's got something called a rover motion counter, which is an array of integer values that counts up for a specific type of motor movement. So it might count up for a turn, or it might count up for moving forward a specific distance. And the rover motion counter will reset every time a sight frame is made, and a sight frame can be thought of as an origin point for the robot. So instead of having the robot being the reference, it'll have a point on the surface of the planet as a reference, which is a little more accurate. And this can be used in conjunction with the telemetry data taken from the Summit system, so it can avoid obstacles and whatnot. That's it. Any questions?
How much resolution does the point cloud get?
I don't know. It's probably.
It's gotta be huge.
Yeah, because it is NASA. They got money to throw around. Any questions?
Just as a side, notice what's the power source for this older?
Solar.
Yeah, it's solar. And what's the new one?
Yeah.
It's got a nuclear reactor on it.
10 pounds?
How long's the life for the new one? Generally, it's like 50 years for nuclear reactor.
Yeah, it's pretty long. It's almost equivalent as long. John, go ahead.
You gotta go 2 back.
Oh. I was like, this isn't long. My bad, I was on the phone. Today I'm going to be talking about the new military mapping, 3D mapping. Obviously, everyone knows unmanned ground and then UVAs, which is unmanned aerial. Right now they have, when they fly by, they have the 2D mapping. So when it goes over, it takes pictures or video of it flying over stuff, but it doesn't say how far it is away and things like that. And then now they're moving into the virtual 3D mapping, which as it goes forward, say in a city street or building, it goes through it, and as it's going through, it builds a map simultaneously and then gives it back to the soldiers.
So before they walk in, they know kind of where the enemies are at, the layout of the streets, the layout of the buildings, and all that stuff. That way they're not walking in blind. So it's actually really a safety kind of thing for the military. It uses flash LiDAR and stereo vision, which pretty much takes pictures and then maps it as it goes around. And then obviously the flash LiDAR is saying how far it is away with every picture, so that way you can actually draw the 3D map with the measurements and everything. Any questions?
So I'm doing a presentation today on online SLAM in dynamic environments. And the basic need for this is that, as everybody knows, most environments are not static. You know, walls normally don't move, but other objects usually move throughout the room. And the way this does this, it uses a quality filter to estimate the robot's position at landmarks. And from this, it generates 3 separate maps. The first map it creates is a static map. And then it also creates what's considered a dynamic map. And the second map is compared to the first one, and the objects that have moved from the first map are considered to be dynamic. And from those dynamic maps, for the dynamic map, it can take and do another scan to create a third map for localization. And the objects that are moved are thrown out, and it keeps the static points as landmarks. And as you can see, this is the first map that it creates. And you have only your walls and doorways that show up. And as you see right here, there's 2 objects that are picked up in the dynamic map. And then the 2 maps are combined, and you have the robot and the person in this case in both maps. And that's it. Any questions?
Salazar, and I want to talk about occupancy grid mapping, OGM. Occupancy grid mapping was first introduced in 1985 by Hans Moravec and Alberto Elbes at CMU University. It's a pretty simple concept. All it does is mapping an area using a 2D array that is specified by the programmer. So you specify how big is the array and what's the size of the cells. Typically, the size of the cells is between 5 to 50 centimeters. For this to happen, the robot must know its location at all times. So that's a prerequisite. Because the sensors are very noisy, the reading from the sensor has to be put into the probability function that uses the Bayes law, which is the probability that an event A occurs given event B. So when the sensors read the data put into the function, and the probability determines if that cell is occupied or not, and then you put the value that you specified there. For instance, you can put maybe 0 for empty, 1 for an obstacle or something there, and then you can put maybe -1 for cells that haven't been checked yet. Typical sensors that are being used for this are the ultrasonic, infrared, laser sensors. Pretty much those three are the more useful. On the right, I got a picture of this test that they did using UPack robot. And as you can see on this picture right here, the little dot on the center, that's the robot, is loaded with 8 infrared sensors. And the picture on the right, the farther right, is what the mapping came out to be. And any questions?
How did it map that section inside the that little section DOS part?
Well, the robot moves. So it starts, let's say it starts location 55.
There's no opening, is there?
No.
No.
How did it get in there to know that it was just a wall instead of a solid block?
That was figured out.
Smart robot. Yeah.
I
use baseball to predict it.
On the area, the old
Probability that it's closed.
Yeah, if it's closed, then let's assume that it's empty.
Why wouldn't you assume it's solid?
Yeah, why wouldn't you?
That's a bad assumption.
Because it was a computer.
No, they got it right.
Any other questions?
Oh man, I just got to take off some points for that then. All right.
That's right.
We're trying to brush it away and go on.
All right, good afternoon. My name is Benjamin Rose. I'm going to talk to you a few minutes about ROMS. It's a pretty short acronym to actually go through. It's remotely operated autonomous mapping system. I'm going to focus more on the actual mapping than the actual robot itself. It's on a standard platform with infrared sensors, sonar sensor stuff to keep it, situationally aware while it's traversing through the halls and stuff. But I'm going to focus more on this new 2D/3D LiDAR technique that people at Stevens Institute of Technology actually has developed. What makes this unique is the 3-axis actuator that actually turns the 2D LiDAR, the very inexpensive, relatively inexpensive 2D LiDAR, for obstacle avoidance. And it's actually a lot cheaper than most multi-LiDAR systems like we saw in the DARPA challenge. But also, when it stops to make a 3D map, it actually turns the 2D LiDAR so it can actually make a 3D map. Now this is worked in conjunction with the video resolution like we saw earlier in a previous presentation, that it actually lays over the video image on the LiDAR image. That way you get a full color 3D mapping image. Currently, ROMS is in a semi-autonomous and autonomous state. You can actually do GPS point A to point B, and it'll map out the situation or the building wherever it's at. Or an operator can actually remote in through like a network. This is sped up. Latency times are very small on their home network. Also, these guys at Stevens Institute of Technology actually made their own operating system for this, the OCU, as you'll see here. The first thing you'll see here is the middle picture, picture marked 5 is the reflection intensity parameter produced. This is basically all at nighttime, so this actually can be used for like military applications where this goes in before the team goes in to actually map out the situation. I have a short video. This says in the matrix, but you really can't see it. But I thought this was pretty neat to show how this robot actually traverses through the hallways and produces a 3D color image of what's going on. This is actually at their institution, going into Design and Manufacturing Institute. So basically this whole university is like MIT, except it actually markets what they're making to the general public. So some applications for this would be, for instance, surveying. So imagine that you're a surveyor, can't get to multiple locations. You can deploy this robot, have it map out your location. That way you can see how to do the demolition or construction. So some applications like this are very helpful. Any questions? Thank you very much.
I'm going to be presenting SLAM using dual frequency identification sonar, otherwise known as DIDSON. It's an acoustic imaging sonar. It's most commonly used by oceanic salvage companies, treasure hunters, Army Corps engineers use it a lot, and geologists also use it. Some applications that this SLAM software uses: ship hull and infrastructure inspection, marine structure inspection, underwater survey, and navigational-based mapping. I have a snapshot here of a 3D image taken from the underwater, I want to say UAV, but the underwater vehicle is autonomous. What this is, it's 2 bridge columns. So this thing pretty much mapped 4 out of 5 of these applications, like a marine structure inspection, it's an underwater survey, and navigational base mapping, basically all wrapped in one. I thought that was pretty cool. The procedure used, SLAM uses the data and statistics acquired from the onboard sensors and the DIDSON. The sensors are the DVL, the dot wave velocity log, depth sensor, and obviously the DIDSON. The sensors in the DIDSON combine to create 2D and 3D maps of unknown objects and environments. And the SLAM procedure improves accuracy of existing maps by localization and not relying on external infrastructure. That's about it. Any questions? Nope.
I'm going to be presenting real-time stereo visual SLAM. And as we all know, SLAM gives the ability to navigate through an unexplored environment and to actually locate where the robot is within that environment. The most common SLAM sensors are laser ranging systems, sonar, inertial, as we've had previous presentations on, the visual, and then the visual sensor, which is basically usually a camera that's used. Basically, the ranging sensors are highly accurate, but they're unable to perform object recognition, which is really important in a lot of environments. Especially when you're trying to really understand what you're dealing with in the environment. The sonar, they're cheap and they're very fast, but they're also really noisy at what they do. And that's part of that statistics equation the probability equation that we just heard about, having to do that because the sensors are just so noisy. The inertial, they're useful, but they're not very accurate still. You have a tendency to go back and forth on how accurate they are, or maybe they're not so accurate. The vision and the camera sensors are very accurate. They have high definition now, and they're just a very clean input, so that we can really base what's going on in the environment. So I just want to talk about the stereo visual SLAMs. Basically, when you have 2 of these cameras set up, and it really helps out with depth perception. Just like if you were to cover one eye, you don't have that good at depth perception. But when you have both, you're able to really locate where a point is in 3D space. As far as processing stereo SLAM. First, images are captured using the 2 cameras. Then they're converted to grayscale, and they're undistorted using an algorithm. The scale spaces are then created, usually using Hessian or a Gaussian scale. And the correspondences are estimated using camera projection matrices. These matrices are set up through a calibration that's taken place before the actual robot is being used in the scene. So you can actually know where these points are, have a reference to where they usually are. Therefore, you can gauge where the points are when you're in the environment. Any questions?
Now, sponsor, I'm going to present to you Mini Slam, minimalistic visual slam in large-scale environments based on new interpretations of image similarity. Now, this type of slam is using the previously talked about camera vision, basically be able to use visuals of what cameras see to make fairly accurate, while actually being cheaper than some of the higher grade state-of-the-art 2D or 3D LiDAR sensors. It's typically even better in the longer ranges. Now this is us, and some of it, the way it works is it can make maps that are more accurate even in crowded, cluttered areas. So there's like a pile of trash in the room, it will notice that trash in the room and not consider it to be a wall, for example. And that when it's it uses odometry and omnidirectional camera to do that. The camera supplies information used by a same algorithm, which is then sent off. The estimations for the map are done online using a linear time slam algorithm that operates to make an efficient graph representation. The graphs that are created are more consistent, or very consistent, as can be seen by just how accurate that map that was created by the system. The key points to the approach is that the estimation of the Ho's difference in the relationship does not need to be extremely accurate because of how it works, as long as the corresponding visuals are modeled correctly. Are there any questions?
My name is Jessica Meeks. I'm going to be doing the particle filter-based SLAM. It's basically an algorithm for sensing basically individual particles in order to map out and localize the robot. In this case, it works off of 2 frames of reference: the robot, which is typically sensed through the odometer as to how far it's going. This helps with localization, and the world, which is a laser, typically used a laser rangefinder in order to do the mapping. As you can see from the example algorithm pseudocode, basically it starts off in a predict particle mode, and what this does is it's a huge complicated math equation where, based on past particles or the initial rating of the laser rangefinder and starting off from 0 in the odometer, it maps out what it expects to happen. So as you can see from the simulation over here, it takes a basic map, and this is the end result. For the beginning, you would probably just have a single red line and maybe the first 2 walls there, and it would progress as it goes. And that's basically because the red line, as you can see, is fairly thick. This is a computer simulation, so it's just all the different directions that it can map out based on this process. And so after the predict particle stage, it does the particle calculations and basically what's called the update stage. And what this does is, when it's doing the mapping, it takes each particle from the laser rangefinder data that it sends back, and it weights it. And based on the weighting of these particles, that's how it's deciding how to move, where the walls are, and how thick it is. So based on past mapping, it'll build up its map, and slowly so you get more and more weight, because there will be some outside ranges that won't be there. So it helps to basically cut down on the noise as you're going along, so the map becomes more accurate. And so it adds new particles once it goes, and it keeps looping through and updates the map each and every time you're going through the course. And based on this and the odometer, that's how it moves through, and you get localization and mapping.
I do have a question,
Yes.
and that is with respect to the that red line over there. You notice that it gets pretty wide. It's going straight, gets pretty wide, and then suddenly it gets really narrow.
Yes.
What happened there?
That's basically going around the corner, because it goes up to a point, and you know, it says, okay, we're going straight. But once you get to that corner and it sees that wall, it's going to turn basically at almost the same angle every time. So if it's like, say it's right here, when it turns, it's basically going here, but that's also why this sort of widens out again, is because you're not sure how sharp you're going to take that turn. It's just, you know, it's going to get to this point and take that turn. And I think a lot of it's also to do with like the numbers exactly. I'm not sure how the calculations worked out for that turn.
But I'm just kind of wondering why it looks like there's an almost cliff right there, and it goes from very wide to very narrow at that one point.
A lot of it also has to do with this corner right here, because that cuts in. So maybe it would read that corner as being a little closer, and
Okay.
so it would overcompensate in this areas.
So it is readjusting its knowledge base of where it is and where it's going to go, is what you're saying.
Yes.
Okay. Any other questions? Thank you very much.